see if it works. Yeah, it shouldn't start it. Okay. So I guess for the rest it got too fast last week.
Sorry?
I guess for the rest it got too fast last week. I have no clue. I mean, if it's too fast, they could have told me. But for now, we can just continue with multi-way ANOVA. Are there any questions about last week, actually?
We have a question about one of the exercises.
Yes.
What specifically is about the potency in general, because in one of the two questions, I don't remember which one, it says that the significance was raised at 0.1 because it was suspected low potency.
Yeah.
So in a nutshell, my question would be, what is it specifically that you should look at to guess whether your
whether you can do that, whether you're allowed to change your alpha level.
Well, just to, like, what are the parameters that I should look at? Because in one instance was you suggested to look at the confidence intervals.
Yes.
And in another instance, while looking at the difference in the treatments, that there was not a lot of significance. But in my mind, of course, if there is, it's also plausible that there is no significant difference in
No.
treatments, right?
But that is always, there's no p-value of 0 where we fully 100% are able to reject a null hypothesis. There's always a risk that we have by, using this alpha level 0.05 or 0.1. Whether that is sufficient or not really depends on the field that you're in. Generally though, pretty much any field uses 0.05. If you have to use a different alpha, then that has been very well specified. Like, for instance, you have to set up like a certain study design in a medical field and you have to go through an ethical committee. They may decide, for the sake of using less patients, that a 0.1 level is acceptable or not. But if you don't have any signs of anything like that, it's not clear at all, then you always use 0.05. As far as the effect sizes, how to interpret that is actually a very good question, because usually when people do testing like this, they compare two groups, and if the p-value is below 0.05, they reject the null hypothesis and then they basically conclude that there's a difference. However, the p-value, as you might have realized now, is a bit of an arbitrary cutoff. It's some kind of combination of the biological effect size, how large the difference between two groups is, and how certain you are about these group means that you have estimated, or about that difference that comes from these group means. If you have a very significant difference, it can either mean indeed you have a very large difference between the groups, or you have a maybe very small difference, but you're just very certain that there is some kind of difference. That's something that these tests do not tell you, or you do not differentiate. Whereas with a confidence interval, or just effect size in general, that if you use that instead for your inference, you think more about, hey, even if there's some overlap between these confidence levels or not, do I consider the difference between these groups, biologically relevant or not? You're not just thinking about, oh, this it hits this threshold of 0.05, so there's a difference, and this treatment will change everything. You think about the effect size in general and how much overlap there is between the groups, and potential that these, the difference that you observe may not be there at all if you use confidence intervals. So at least if it comes to me, I like to use confidence intervals for that reason, for any kind of inference. Now I know most journals, they ask for p-values, so you can add simply a bar plot or like your, your curve with a confidence interval and still use your p-value in the text or, between the bars. Both is fine to do, but at least when it comes to inference, I would trust the confidence intervals for that reason.
Yeah, no, definitely. But my question was more like, okay, I conclude that with the data set that I have in my hands,
Yeah.
this is what I observe, but can either keep that as a conclusion, or another is if you suspect low hypothesis that I can increase my sample size.
Exactly. Yeah.
But
And if you deem that effect, I mean, if indeed a small effect matters to you, then you can increase your sample size. But people shouldn't hunt for, they do one experiment and they see like I don't know, a zebrafish larva is 0.1 millimeter taller, that they just collect extra data until that becomes certain and significant. That sort of goes beyond what the point is of all of this, which is to simply conclude, given the amount of observations that you have, if you have enough certainty to conclude that the effect that you're interested in is present.
How can I conclude that increasing my sample size wouldn't matter in improving the significance or the validity of my test?
Yeah.
What would be just looking at if the confidence interval don't overlap too much, would that be a good estimate to infer this?
I mean, so the confidence intervals in the p-value, they are shared, and both are based on this 5% cutoff. So in terms of interpretation, they can be largely the same. It's just that the p-value is like this absolute cutoff of 0.05, and whether it matters or not, that's up to you, if it's made. But with the confidence intervals, even if, let's say, I had, for instance, a case today, actually coincidentally, where some student, he had like a ratio between two groups. So he divided the group mean of one group 1 divided by group 2, and if the groups do not differ, that value would be 1 in this case. So he did a test, and that test was about, I don't know, 0.11. So it was not significant, and he was kind of disappointed about that because he was hoping it was significant. When we actually looked at the confidence interval, so between the groups and that interval, the actual ratio that he got was about 0.7, which was about 30% lower than if there was no difference. But his confidence interval itself, it looked like this, where you have this range here, and then barely it touched the 1. Like just a snitch, it touched the 1. And because this confidence interval touches this 1, it basically means it cannot differentiate between there being no difference and being the difference that you have observed, right? Because it falls within this range of possibilities. So indeed, the p-value was correct. There's no significant difference based on this result. But if it barely catches this snitch, would you then just toss away, this observation and that it barely touches and say that there's no difference at all? You wouldn't. You would still say there is a difference. It was lower, and 30% reduction was indeed for him quite substantial. So for him, it was enough reason to say, okay, then it's just the problem is my effect size or the accuracy of my measurements, or I should optimize this experiment that I'm more accurate to, if this effect is true, to basically achieve a significant threshold to get that one out of my confidence range next time. But these decisions you can only really make based on this. If you just see a p-value cutoff, you don't really think about effect size. You don't really think about whether it barely touches and how much it is in the realm of possibility. That's the idea, and that's also why I think confidence intervals are better. That's matter. Okay. Does that help to answer it?
Yeah, no, definitely. Yeah, sure.
Yeah. And indeed, whether, you can, even if there's an effect size of, because he thought this was substantial enough, and he had another one that was about, 0.8, also another group. It was like this, that was also a bit further along. And I asked him, do you consider this also, biological? And he was like, nah, that's not really, so we found some middle ground of what he would consider a cutoff worth using. And then I was simply able to say, okay, you need a few more samples to be able to replicate, to be able to achieve this then next time. And then you can make some kind of inference on it.
Indeed, I found also very helpful the the function, the plot model one that you showed at the end of that, because also in that one you can really nicely visualize also a little bit the difference with also the confidence interval and
Exactly.
make a bit visual estimate, visual conclusion rather than based on.
Yeah. With EM means, if you do plots, and I can show it maybe at the end. If you do plots and then contrast of your GLM, then it shows actually indeed the contrast plots like this, basically. But if it's just normal linear model, it would be then a 0 because no difference is subtraction. But if it's something like Poisson or binomial where things are multiplicative, then it will show indeed 1 is the center and then the effects are multiplicative. If it's 1, there's no difference obviously, but if it's more or less, then you can derive that from that. That's a great help. And yeah, how much samples you need or what you are interested in at the end of the day, it depends on the effect that you're interested in. And most scientists, they don't really think about it. They just collect data and they just hope it's then significant. But at the same time, that's not really the goal why we're doing statistics. We're trying to build a case if this effect is present, at least as I would be interested in. How would I be able to prove that? That's the idea behind why we do this whole process. Yes.
Thank you.
No problem. Yes.
I have a question. It's not specifically about last week's assignment,
Mm-hmm.
but more in general.
Yeah.
It seems that we're using the LM package for everything.
Everything.
For almost everything. You can just compare means. You can do a t-test. I think you can do ANOVAs.
Everything.
But if I look up the documentation for LM, it doesn't actually, at least when I read it, I couldn't actually find it described, at least in clear terms. If this is your input structure, you're doing this test. If this is your input structure, this test. It just kind of decides what to do on its own.
Yeah, because the LM, it stands for linear model.
Yeah.
And everything that we are doing is a linear. Everything based on normal distribution is a linear model. And what kind of results, it's really hard to sort of specify for LM, which I can understand, for how it treats literally everything that you put into it. Because there's a lot of things that you can model.
It seems like a dangerous situation where if I accidentally put in the wrong type of data, I'm doing a completely different type of test.
Of course,
It doesn't tell me what type of test it's doing, it's just giving me an output.
It's giving you an output.
So my question very concretely is, can I find somewhere a flowchart or something, or like a table that tells me if you put this in, this is the test that you're doing? Or do people just know this somehow? Like, I don't understand where people are getting the information of how to use LM.
By doing statistical. Essentially.
That's not a very sustainable way to...
But there's only 2 ways to go about it. If you have data that is continuous, whatever comes out of it relates to a continuous predictor, right? If you have data that is categorical, what comes out of it is something related to categorical, like difference between groups.
Yeah, but there's a lot of different linear model tests you can do, right? Like a t-test isn't the same as an ANOVA.
No, but at the same time, the only tests you should care about are the omnibus test for model selection to define which of these variables actually explain something about the data, and indeed the post-hoc comparisons at the end. Those are the only tests you would be interested in.
I don't understand what you just said. Sorry.
Well, you say there's a lot of tests that you can do.
I mean, there's a lot of different types of models you can fit using LM.
Yes.
That's what I mean. And let's say I want to do a t-test, but by accident I do an ANOVA. That's what I'm saying, right? Like if I don't somehow miscode my analysis and I do something else, how do I know what I'm doing in LM?
You simply check the summary, because in your summary it shows what is actually in your model, what categories are in your model.
It doesn't say something like t-test results. It says linear model results.
Yes, because everything that you do is a linear model. And basically the test that you're doing, ANOVA or t-test, really depends on the structure of the data. If you have multiple categories, then it becomes the test that you would be interested in is an ANOVA. And that's something you should know more or less from a
But
course.
am I just being very pedantic if I'm saying that a phrase like the test that you would be interested in, then you're leaving it up to the user to know exactly what you're doing and it's not documented anywhere.
Well, if we're gonna go there.
So because
you
I
thi-
actually looked up the documentation, right? So maybe I just
Yeah, no,
not informed enough to understand what it said.
I get what you mean, but if you look at, for instance, comparable software, like I don't know if you know GraphPad Prism, which fully automates this process. You just toss in your data,
Yeah.
you click a button which says ANOVA, and it will give you an ANOVA back.
But then I know that I'm doing ANOVA. So my worry here is that I can use the LM to do a t-test, to do an ANOVA, to do other things.
You're right, you're doing an ANOVA, but you don't know if you're doing the ANOVA correctly, because you don't verify whether the ANOVA is fitting. You don't know what it's actually comparing. That's the things that are, well, at least having to control yourself about what you put in your model and the comparisons you make also makes you understand way better what you're doing. If you leave it up, you just toss it in a program in a black box and you leave it up to them to decide, you might also get different results and even understand less what you're doing because you're just clicking a button.
No, so I agree with you that it's good that we can specify these things. But actually I feel like this LM function is smartly deciding what to do without telling me what it's doing. And that's what I'm worried about. Do you understand my problem?
I get it, but it's really not very smart in that aspect because at the end of the day, there are just two types of variables that go in there. Something that's continuous and something that's categorical. A categorical variable, if it has multiple groups, then you can do an ANOVA, you can do a t-test, but the only thing that it's doing is saying, hey, these groups, this mean is higher with this mean is lower with that. The type of test that you do is simply the same as if you were to click a button in a program. You have to decide for yourself if you perform the ANOVA table on this model, if you perform pairwise comparisons on this model. That's up to you in the end. The only thing that it says by a summary is saying, hey, these values in this groups are overall higher or are overall lower, or this regression coefficient is going up or going down. It's not necessarily deciding the test for you, you still decide that yourself.
But if I do it, I can do a t-test with LM. I can do an ANOVA, I can do a linear regression, right?
And you can also do that with other programs like GraphPad, right?
No, so so I don't think I'm correctly explaining what I'm worried about.
That you have too much freedom in deciding what test you're doing.
No, I like the freedom.
Yeah.
I don't anywhere see in the output that it tells me what exactly I specified it to do.
It does, but maybe with multiware ANOVA I can specify it a bit better, how it shows that actually. Because I will also show summary outputs, and maybe from that you can get an idea of how it specifies this.
Okay.
Yeah, we can just try. Like at the end of the day, I think, at least that's my personal belief, I don't like having people just having data, toss it in a model and let a model decide it. You should understand this yourself and not,
I totally agree with you, but to me it seems like LM is doing exactly that. You're just putting it in, and then LM, based on the structure of your data that you put in, it's doing a specific type of analysis.
Yeah.
You're not saying do t-test, and then you put in the data, and then if the data structure is incorrect, it just gives you an error.
But it's not doing a test, that's the thing though. The test you decide yourself, it's only deciding how it breaks down the data into what the effect sizes are. If one group is higher or lower, it's not doing any tests. That you still decide for yourself.
I'm fundamentally misunderstanding what LM is. But okay, so
yeah, we can just try, see if it with multiware ANOVA it becomes more clear. Any other questions? No? Otherwise, no? Okay. Then we can just start with multiware ANOVA. So we can recap the same example for last week, because last week we were talking about the guinea pig example, where we had two treatments, OJ, orange juice, and VC, vitamin C. And we want to know if there was some kind of difference between them, because the orange juice was infinitely cheaper than the vitamin C supplements that they've been using. And they want to know if it has any effect on their tooth length specifically. And if they could interchangeably do it. Last week we tried to model this using an ANOVA, treating those as a continuous covariate. these are after all numbers, so you can just draw a line and see if these lines cross at some point. And if you know they cross, which they did at about 2, then you know at that point they would have the same effect. However, as someone already last week quite smartly picked up on, these are 3 very specific doses that we used. Why not simply use them as groups? We could say a dose of 0.5 is low, dose of 1 is medium, and a dose of 2 is high. And there's indeed no problem with that. The only thing is that the kind of model that you get out of it and how you interpret coefficients in the test from this will of course slightly differ, which will in turn be what we call a multi-way ANOVA. So how does it look if I plot it basically as a factor? Then I don't see a line anymore. I just see groups of those, so 0.5, 1, and 2. I see OJ and vitamin C, as you can see here, colored. And I can already see similar things like last week, where OJ was consistently led to a higher tooth length compared to VC. However, at a dose of 2, the tooth length was relatively similar, if I would give them that. Whether you want to model this as some kind of curve, or whether you want to model this as groups and then just compare whether these 2 groups are different, is completely up to you. Because in this case, the advantage of using something like the multi-way ANOVA, treating those as groups, would be that I don't need specifically a linear relationship between those and my outcome. As you could see from OJ, at some point, there was some kind of asymptote going on. The effect was diminishing. And if I use my standard linear model, draw a line, I can't always properly capture that. There are of course tricks that we can do. Instead, we could use the logarithm, or we could even fit a quadratic function or something like that to capture this. However, why not make it simple? Just don't assume any kind of linear relationship. Treat these as separate groups. It doesn't have to be the same continuous line. This group can completely differ from what this group is. I'm only interested to see pairwise if there's some kind of difference between the groups. And there doesn't have to be a specific linear relationship between those and the outcome. There is a relationship between those and the outcome, but it can be whatever it wants. If those one can be a lot higher and with those 2 drops, whatever. It can easily fit that because it sees it as groups, not as some kind of continuous factor that it has to account for. Doing so, however, you still lose a little bit of information. I'm not able to make some kind of inference about what would happen if I apply a dose of 1.5 or a dose of 0.75, or maybe make predictions if my dose would continue after that. I lose a little bit of information by doing this because I don't see the whole trend. I just treat these as separate groups, and that's also why it's sometimes a bit more trickier to interpret it in terms of making predictions for other things that you would have modeled here. So that's kind of a disadvantage. However, that being said, a lot of people still, at least in molecular biology, they use a lot of multi-way ANOVA for that reason, because it's very flexible to model your data with. So how does a multi-way ANOVA look, or how does it start? The idea is that instead of just one group with multiple, one variable with multiple groups, we this time have 2, and each have their own independent effect. For instance, here I have an example where an outcome is decided by the genotype and a certain treatment that you do, and I have then basically 4 combinations that I can have. I have no treatment control with just the wild type genotype, I have no treatment with mutant genotype, I have treatment with wild type, and I have the treatment with mutant. And what at the basis I would just, if there would be no relationship between the genotype and the exposure, is simply that these 2 effects they stack. Mutant increases whatever outcome I am interested in, maybe muscle mass or something like that, they are beefier. Treatment maybe also do that. As you can see, there's some kind of effect added on top. So if I apply my treatment in the mutant mice, then these 2 effects simply stack, and whatever mean I would predict would be there is simply whatever I already started with plus the sum of the independent effects. The same is also if I would have a negative effect, mutant reduces actually the muscle size in this case, then I would remove that, and also I would remove that in the combination. These 2 effects will be independent, at least based on this model. It's also what you can see in the formula, or you would describe it. You have some kind of intercept. Mice always have some kind of muscle, at least as far as I know. There's an independent effect of one covariate, which would then be, in this case, genotype, and there's an independent effect of the other one, which would be exposure. And they simply sum. So if I perform my LM, my linear model, I can indeed simply do it like that. I have my outcome, len, the length of the tooth, which I explain based on supplement and dose. So two independent factors. And important is that dose, this time, is not a continuous covariate. I made it as a factor. I see not 0.5, 1 and 2. I see a group 0.5, a group 1, and a group called 2. And that also changes your outcome. Before, I only saw dose as a single covariate, because it only represented the slope, which is applicable to all these three different slopes. What the actual effect of dose was the actual value of the dose, 0.5, 1, or 2, multiplied by that effect. However, now there's no continuous relationship. Each group can have its own mean. So we start with 0.5 intercept, and if I go from 0.5 to the dose of 1, I have to add 9.1. If I go from 0.5 to dose of 2, I have to add 15.5. And that is also important, as also what you said, how you would have to check if your data is loaded incorrectly. If I see that these doses are treated as categories, which you can easily see because they have their actual category names, then I see category names. If it's treated as a continuous covariate, there's some kind of line, and this will be the slope of that line, then I would only see dose. And that is at least a check you would have to perform yourself to make sure you're dealing with a multi-ware ANOVA instead of an ANCOVA in this case. Yes?
So, can I continue on my question earlier?
Yeah?
So, this is an LM,
Yeah.
right? And this is now an ANOVA output.
Yes. Well, and what do you mean by ANOVA output? It's simply what we call coefficient table.
So this is not the ANOVA that we're doing yet?
Exactly.
So we're still going to do the ANOVA, is what you're saying?
The ANOVA is the actual test, and the test you decide yourself. The only thing what LM does, it is breaking down data points into effects explained by supplements and effects explained by dose. If I had this, this single guinea pig that had a tooth length, let's say I had a guinea pig that has a tooth length of, 30, and that guinea pig had OJ of, had a supplement VC with a dose of 2, that means that it starts at least, the tooth growth starts at 12.5, and that's the intercept, 12.5. So part of it I know is because they always start at 12.5. Part of it, why it's this high, is because they're in group VC. Which was lower, but fine. So part of it is due to being in group VC, I have to subtract 3.7 in tooth length, it will be overall lower. And part of this is explained, this data point, as having had a dose of 2, which adds 15.5. So in total, if I sum this all up, which is a bit annoying, let's see, 2.5, this is 27, now 28, 25, 24.3, 24.3, that it's being this high, 30, is because of the sum of these effects. Why it is not exactly 30 is because there's still natural variation. It's some guinea pigs, regardless of which group they are in, they tend to have longer tooth length and some have shorter tooth length. The only thing that the linear model does, based on the structure that you have provided, is breaking down data points into individual effects. Part of the effects are explained by dose and supplements, based on the structure that you have provided yourself, and part of the effects they're not explained. And the actual test that you're doing, based on the structure, you fully decide yourself. That ANOVA table and the post-op, you can fully design yourself what comparisons you want to make after your model has basically broken down these data points into effects. That's also why I'm so insistent on, It's still your own choice which test you do afterwards. You are still right though. You have to understand how to specify your model correctly. If I misspecified those in this case as a continuous covariate, then I wouldn't do my multi-way ANOVA anymore. Then I wouldn't see it as a factor. But that's something I can't bring it otherwise. You have to learn that by yourself.
How did you specify that dose is a factor here, not a continuous variable?
I made it actually a factor. I probably should have shown it in the first slide. So I told R, if I did my summary from last time, you saw that the dose had the same like values as here. It has a minimum, medium, and a maximum medium because it is continuous, it's numeric, it's numbers. Whereas if I say factor of those and I just overwrite that, it's looking for unique groups instead of continuous covariate. Of course, this works here very nicely because they had very nice experimental design where they had neatly 10 groups, 10 combinations between these factors. However, if I have, let's say, I measure randomly hydration, for instance, those are all very specific numbers. So that wouldn't really work with that because then I get a whole list of different groups. And yeah, whether you want to go for an ANOVA or a factorial ANOVA or multi-way ANOVA is up to you in the end and how you structure this yourself. Yeah. So yeah, whether it's seen as a factor, you have to specify that. And yeah, there is room for error in that.
And then maybe one final question that maybe then not a good question, but then can you go back to the slide you showed?
Yeah.
If this is not the ANOVA, then where are we doing the ANOVA? Or is that still coming in the slide?
That's still coming. Okay. This is just the whole thing, what I'm trying to show here. Also because you guys wanted to know where data points, where these things are coming from, is how these kind of models that we use to do the test, that we use to perform the contrast, make these comparisons, how they break down data points and how they look at your data, and to see if it also meets certain assumptions. Because if, based on this, I would have a certain distribution of the unexplained variance, if that is not true, then all the tests that I will do based on this are also not true. And with programs like, for instance, GraphPad or SPSS, you can actually do that too, I noticed. But it's sort of hidden, and most people, they don't do these tests for that reason. Or, well, there's at least one. They show the Shapiro test at least. But like the actual Q plots and seeing what happens, they actually don't even check that. They just toss their data in a black box and the values get pooped out, and you don't even think about whether this was a suitable fit of what your data entails. And here you have to actually think about it, model it yourself, and once you indeed find the model, good for your data, then you have to do the test, just like you would do in a program like that. So yeah, you have an extra step doing that, but that also means you understand way better what you're doing instead of tossing it in a black box and the test gets popped out, basically. Yeah? I can also fill this in for the rest. Actually, I will do it so you guys have an idea of how data points are broken down. So, you can just simply do it for each of the combinations. So if you remember, I had 3 combinations, 0.5, 1, and 2. And then I had OJ and VC for each one of them. So we can calculate based on how the model broke the data points down, we can build it up just to see what the predicted means will be. Of course, it's not something you have to do, but then at least you understand the output a little bit better, where it's coming from. So the first group, or first groups I should say, are always the intercept. The reason for that is if I have an intercept, a starting value, and I then have to add from the starting value a difference with 0.5 and a difference with VC or OJ in this case, it would cost me 2 extra degrees of freedom because I would have 2 extra estimates. And as you hopefully have understood by now, we don't want to waste degrees of freedom because if we run out of degrees of freedom, our model is not going to run anymore. We need to save them. So what have we cleverly decided? The first combination of groups will be the intercept, which makes sense, right? Because there can't be only a VC intercept, it is VC in combination of one of these groups. So in this case, the first combination, and this alphabetically, will be for supplement OJ, O is first, And for those, it will be 0.5. You can easily see that because they're nowhere else in the table. So that is, in this case, the first group. And that starts with, what is it? 12.5. Let's say this is 12.5. So here, this will be the mean of OJ at 0.5. If I then want, instead of OJ, I want VC, I have to remove 3.7. See, if I go down and I look for anything related to VC, if I want to go from OJ to VC, I have to remove 3.7. It's a reduction. So in this case, minus 3.7 would be minus 9, 8.8. That would be the mean of VC at 0.5, because I'm not changing the dose, I'm only removing the effect of VC. Here. If instead I still want OJ but with a dose of 1, then I have to take again my intercept, and instead of 0.5 I want to go to 1. So I have to add the effect of 9.1, which is associated with a dose of 1. That's the difference in this case. So then I go from 12.5 to, what is it, 21.6. If I go from OJ 0.5 to OJ OJ 1.0. But what if I'm not, for a dose of 1 would not be interested in OJ but for CC? I have to, again, like before, these are separate effects. I would also have to subtract 3.7. It would be about, what is it? Then minus 0.1, no, 18, 17.9. 17.9, yeah. For the last one, you can understand yourself, right? If instead of a dose 0.5, I would be interested in a dose of 2, then I simply add the effect of a dose of 2. Note 1, it's always based from compared to the intercept, the difference. So in that case, I will have to add 15.5 to this, which will be 28. Then if I want to go for a dose of 2 with VC, again, I have to add then the dose of 2 and subtract that effect of VC, which leads to about 24.3. So this is how, as you can see, R broke down your data points, your individual data points, in effects that are explained by the difference between OJ and VC, right? It's always a consistent difference between 4 of 3.7, and the difference between the doses, which is, as you can see, also consistent regardless of which supplement or which dose you're looking at, or sorry, which supplement you're looking at. And all those two always goes up with 15, regardless of which supplement, but the difference between the supplement is always a consistent reduction of 3.7. Yes.
But that's also like a restriction by the model now, right? That
Yes.
the difference has to stay constant.
Exactly.
Yeah.
And that's also what you would do if you throw it in something like GraphPad. It also does this under the hood. The nice thing about here is you see exactly how it breaks down the data point and how group differences are shown. That's the nice addition of just pulling out the summary table. It's not something you have to do tests on or reports, and I wouldn't even consider those tests because they're not adjusted for multiple testing, but it's nice to understand sort of where data points are coming from. If you see a certain difference or not, is that because it's understood well or not, you know? That's the idea behind this.
And so, I mean, I'm probably going ahead here, but if we would have increasing variance of like with increasing dosage,
yeah,
then would, how would we incorporate?
Yeah. So that's the tricky thing. If we assume just linear model, we assume that the variance is constant. Regardless of what group I'm looking at, the variance should be the exact same. And in this case, it also shows the variance or more the standard deviation. And I don't know why they call it, well, I know a little bit why they call it residual standard error, but this is the residual standard deviation. So this would basically be the standard deviation expected for each of the group. So that will be about 3.3. 3.8. That is the standard deviation that it would expect for each of the groups. And that is simply, that's also why it's an assumption of ANOVA that the variance is equal. Because like you say, if the variance would increase with the mean, like for instance with Poisson or binomial, then this doesn't hold up. And if you do it indeed like in like one of those other programs like GraphPlot and all that, I'm not trying to bash them, but the thing is they assume this, they don't show this as a singular value or anything like that. But it is also what that model in GraphPlot and all that is assuming, that the variance for each of the groups is exactly 3.8. And they only offer linear models, not Poisson or anything like that. So yeah, if your variance is unequal, then you're stuck kind of there.
Yeah.
Where here with R you can go with a Poisson or a more suitable model.
Yeah,
model
but then
the
LM
variance.
isn't, because it's not a linear distribution anymore, then you would have to go beyond that.
Exactly. Then you have to do GLM or any kind of this model with a different type of exponential family.
Yeah.
However, that being said, the reason why we still use an other software like GraphPlot is pretty much 90% of the cases are still fine to assume. And of course, realistically looking, there is always some deviation from this. There may be some
But
effects,
it's more
but it's residual enough that it doesn't affect their interpretation and outcomes that much. We still have what we call central limiter, as long as we have enough data points, things start to look normal anyway. So they're not that super concerned, and that's why we still use these models generally. Yeah.
Is it relevant that in this case the standard deviation is bigger than the supplement effect?
Well,
Like, can we
yeah.
interpret?
It is partially relevant. However, the only thing that is telling you is that on average, a point differs with 3.8. But if it doesn't, partially having high variance makes it harder to assess if there is an effect or not. But if you still have enough data points, even though there is a large variance, it doesn't matter in practice, right? Because you have a lot of data points that show that even though there is this large variance, the effect that we have here is still consistent. And although I'm not too always interested in these tests, but these tests are simply a comparison to see if these estimates are equal to 0. So even though we have had a variance that is almost, or standard deviation that is almost as large as the effect or the uncertainty that we have is so small, this effect of 3.7 is still significantly different from 0. So yeah, even though you're right, the how you said spread is almost as large as the effect, it is quite consistent, the effect, given the number of observations that we have. Yeah, it's a good catch. Yeah. Oh, and this was it filled in. Well, I can check, but I assume we all did it properly. Okay. Now that we have fit the model, the only thing that we have done is simply break down the data points into independent effects. But we don't know if our model did that properly. And for that, we have to perform model diagnostics to see if the model did capture this very well. And we have certain assumptions that help us to identify whether, the model has captured this well. This first one, obviously, linearity, from last time, that if we have a continuous covariate, the relationship between that continuous covariate and the outcome is linear. I mean, for this one, you can also still interpret it. It shows the fitted value, so the expected group means, as you can see here, with 6 combinations, each with their own group means, against how much spread there is within the group. And we would expect, even if we're dealing with groups, that roughly there's no, pattern going up or down. Generally, it is in the center of each of the groups. We see, however, one group here that is modeled not too well. I also know a little bit why. However, being honest, I wouldn't be too worried just seeing this. But then again, we're not really looking at, linear regression or anything, so I'm not too interested in that plot anyway. If I look at my QQ plots, generally it looks well. However, there's still something in there, and that's always these are the kind of patterns that I tell you to pick up on, either on the tails that really consistently a tail deviates, like falls off, or if you see spikes in here. If you see consistent a staircase, that can be because you have discrete data, things that are not rounded, and that's why these values they differ with a certain amount. But if you see overall everything's continuous and you see a huge spike, it means one of the groups likely is not properly modeled. So that's overall, yes, it follows a normal distribution, but the spike tells me something may be wrong, at least. But it's not good enough to say, oh, just toss all the model away. Scale location plot, which tells me something about whether the variance is equal, consistent. Like I said, we expect that the variance in each of these group, or sorry, standard deviation, is about 3.7. Is there a question? Or? Hey.
My charger. Oh yeah, my charger.
You have it here?
Ja, daar.
Ah, kijk.
Sorry. Er is nog net, dit ga ik vast vergeten. Maar daar weet ik verder niks mee.
Kijk eraan. No problem. So we assume that the variance is roughly equal between the groups, all 3.7, and I mean, we can quite clearly see that, right? The line gives a good identification that there's no up or down in the variance. Regardless of which group I'm looking at, the variance tends to be equal. The reason why it's not exactly same groups, but instead the fitted value or the group means, is because it's nice to see if the group mean increases, the variance would increase, which would be something like a Poisson or binomial problem, which then you would immediately recognize. If you just show groups means, you can't always immediately link, oh, that group was higher and that's why it is. But now you would see a pattern going up or going down, and you know that there is some kind of relationship between the variance and the mean that you're not capturing. But here it is constant. I mean, yeah, I'm not worried at all.
What are the numbers on the x-axis here?
Here?
Yeah.
The fitted values. So what group mean you would predict for each of the data points? So what value, like I said, I had this data point of 30, right? A guinea pig that was from this dose and had this treatment. It would have predicted then, I think, 24. So that would be its fitted value. But the actual effect would be about 6 larger, so it would be somewhere like here. That's the idea of it. That even though there's some variation, overall this group mean should be relatively in the center of this. And the last one is that there are no influential outliers. That you can simply see if the value is larger than a certain number of standardized residuals. Usually go about 3 or 4. But there's also what we have a line, Cook's distance, which I talked about last time. An outlier by itself is no problem. Outliers are normal, right? We deal with a normal distribution, and an extreme value we can sample just purely by that. What I'm always worried about are what we call influential outliers, which you can see if they pass what we call a Cook's distance, which is this line on the side, which means that they are influential. That one data point is actually pulling by itself the group mean up or group mean down in this case, but we don't see anything like that here. We don't even see the Cook's distance interval. Yeah, so that's it also says Cook's distance here, but yeah, you don't even see it in the plot, so I can't have an example of it. And the last one, and that's purely your own, because we can't really test it. I mean, you can sort of see it, because you see clusters in the data that you cannot explain why they are there, but it's purely from your own, it's what we call independent observations. We assume that each sample is unrelated from another sample. Everything that differs between these samples we have captured. That some data points are higher could be because they have higher dose or a higher supplement. But if there's some kind of underlying relationship that you're not capturing, maybe guinea pigs that were in the same cage and the cage was shaken and that's why their tooth are maybe shorter because of the stress, or maybe some other underlying relationship that you're not capturing here, then it could also explain why some of these values are not completely modeling what you think that they are. And that's simply something you have to realize from experimental design. And if you work with observational data, epidemiological studies, you may not even know that this is present unless you happen to, monitor this kind of variable. In experimental setups, you can of course completely control these kind of relationships. So overall, I wouldn't be too worried about this data itself, but I do say that this kind of spike in here is worrying me. It's a pattern that is underlying. Based on this, what I've told you now, this is the best model we could fit. We can do inference on it, and that's the end of the day. But maybe we can explore why this is a little bit further, so I understand my data a little bit better and get a more accurate model. Like last time, you also have tests, if you like that. As you know by now, I don't like tests because they are just an all or nothing question. But you can still do them. So the first test is Shapiro test for normality of the residuals, which is almost significant even. So yeah, this spike is indeed quite harm to that, you could say. But again, I just look at the plot. If you want, there's the test. You have the Bruce-Bacon test or any other variance test. Bruce-Bacon is quite known for groups or combination of groups to see if there's constant variance between the groups, which, as you can see, there's no violation. It's not, the variance doesn't significantly differ between the groups, which is indicated by the no significant difference. And the last one is the outlier test, which, as you can see here, after multiple testing correction, there's no significant outlier. There's no point that significantly deviates. The largest value is 23, which you can see here. But as you can see, this one after correction also does not significantly deviate. So I'm not too worried about this model, although by itself, maybe something we can explore more if we can capture the, the data a little bit better.
Why are some of those tests studentized? What makes a test studentized?
Studentized means that we work with data that has a specific scale, so length in millimeters. Studentized means nothing other than transforming it to a normal scale, the standard normal distribution. So the mean becomes 0, the variance becomes, or standard deviation becomes 1, and then it models each point accordingly to that new scale.
Why wouldn't you call this normalized?
You can. Studentized, normalized. They're very, they're used quite interchangeably, at least in these models, I know.
So is there like some historic, okay, sorry.
You can, if you want, you can look in the...
What makes this more like a student? But anyway, so maybe
I can't tell you. I at least know it's normalized. And the reason why it's normalized is that it's more broadly interpretable. A standard normal distribution, you know that about 68% of the data is within one standard deviation. 95% of the data should be within 2 standard deviations. So if indeed you're outside of this 2 or even 3, which is 99% of the data, you know that these data is only 1% of it and should be quite extreme. So that's more easily interpretable than doing this on your standardized scale. That's the idea behind it.
Yeah.
But yeah, why they call it studentized instead of normalized, I don't know. That's jargon. So to ANOVA, and now we get to the actual test that we will be interested in. What we have done so far is just break down the data points into effect sizes, but now we can use these effect sizes to build up basically towards a test. And the test that we are usually interested in first is what we call the omnibus test, which is the ANOVA, ANOVA table, which is a general test to see, is there any difference between the groups? Are there any difference, or all these groups tend to have the same mean? The idea how it does that is that now we have, as you can see, models and all these different group means. But what it does is it's going to compare all these original group means to what we call the grand mean. Let's say all these group means were the exact same. There was no difference between the groups. Then just having this one singular mean, which we call the grand mean, should be enough to explain all my data. However, if these groups differ, that means that the overall difference between those group means and grand means differ, which means I explain part why these data points are higher or why they are lower, because the group means are higher than the grand mean or lower than if I were simply pull everything together. That's the overall idea. Yeah. We divide that in how much variance we explain, by in this case supplement or dose, which is sum of squares of explained, and how much of the variance, sum of squares, sum of differences, is still not explained. I cannot explain why a guinea pig is not exactly 21.6 based on this combination of variables. It's a bit higher. And that's the difference between the mean and the group. If I simply square that and sum that for all the data points, that's the amount of variance that is not explained. And the amount of variance that is explained is why this guinea pig is overall higher than the grand mean, which is because it is in this group, and this group has a difference with gram mean that is larger than this. So I can also simply sum that, or sorry, square that, and sum all these differences, which is how much variance is explained by either supplement or dose. Yeah?
So it's not interested in the different those values here because it's always looking at the grand means difference to each of the doses that squares that, sums that, and that's
That's the whole idea of it. And the larger the difference, if there was no difference between the groups, they would all be probably on the grand mean because there's no overall difference. So this value would be close to zero. All these differences, and that means you don't explain values. So the sum of squares will be close to zero. If you divide it by, in this case, 1 to calculate the mean explained variance, it would also be close to zero, and your f will be close to zero.
And if the dose values corresponding to 1 would be I don't know, a lot lower, like under the grand mean, then we would have already taught that in our evaluation of the linear model.
Exactly.
So this happens afterwards once you know that the model checks out.
Exactly.
Yeah.
You'll be aware though, because let's say I have 20 groups and only one differs, that kind of averages out all these no differences from the grand mean and this one that happens to be different. So be careful that indeed it doesn't automatically mean that if this test is not significant, nothing is happening, you know? But it can tell you already sort of preterminally if there is some kind of effect, if these groups tend to differ, or I can already stop here with my analysis, which is quite parsimonious. I don't have to go through all these pairwise comparisons. If I see generally there's already no difference between these groups.
Okay.
And it helps you to sort of, if I have a lot of, if I work with observational data and I have many different effects that I want to assess, I can in one overview see which things are worth further pursuing, doing pairwise comparisons, and which things are likely not of interest to further examine. That's a nice overview. I do it, of course, now with 2 variables, but you can add as many variables as you want as long as you have enough observations.
Okay. And can you tell us again how you interpret the results?
Yes. That's actually, I want to do also by singling them out, because the whole thing, like I said, is that these 2 effects are independent of each other, right? I have an independent effect of supplement and I have an independent effect of dose. So part of the variance is explained by the difference in supplements. You see, if I toss, all the supplements together from all the different doses, yes, there is a lot of variance. As you can see, there's a lot of spread and they overlap. But you do see a difference between the 2 groups consistently, right? VC is consistently lower than OJ. So what can I say? If I draw the grand mean, which is here about 19, I see that the mean of, I think OJ is about 21, is consistently 2 higher. And the difference between this group mean and the grand mean is about 2. And if I square that, that will be about 4, right? That will be my square sum. Or sorry, just the square difference. The same I can do with VC. I see consistently that this group mean is about, compared to the grand mean of about 19, I think it's about 17 then, I would say, which would be about also 2 lower. And if I square that, it would also be, in this case, 4. Now you have to think, because if I were to simply sum that, that doesn't add up exactly to 205, right? But why does it do add up to 205? It's because I do this for every single data point. Every single data point says that, hey, the reason why this data point is higher is because it is within this group, and this group mean is higher. So I have to multiply this by the number of data points, which is 30, which 4 times 30 is about 120. And again, 4 times 20 is also by 120, which of course is not exactly this, because I just simplify this whole process. But it does indeed add up to the total explained difference. Yeah? That's the idea. There is a difference between the 2 groups. It explains why there is a difference between the grand mean, because this data point is in that group, it tends to be higher than if I would simply pull everything together. And that, in a nice convenient way, I can sort of sum. And the larger this value, the larger the mean squared of explained variance, and the larger your f value. And the f value, if you remember from last time, the larger the f value had like a distribution like this. How larger the f value, the smaller the chance you find it under the null hypothesis. So you would reject it in this case.
Yeah. So if your standard deviation of each of these groups would be different. Let's say there's one like for 2.0, the standard deviation is a lot bigger.
Yeah.
That would then affect these sum squares a lot more, right?
Exactly. Yeah.
But it might still not be apparent in the model evaluation because you could still have like all the properties for the linear model accepted, right? So
Yeah.
how would you notice something like that there's like quite a lot of variance?
So you would note by that, well, first you could say, because there's a lot of variance, there's a lot of unexplained variance, so this becomes very large, and even though you see a difference, it's not significant afterwards. But that's also why we have to do our model diagnostic first.
Yeah.
We're only allowed to interpret these tests if we are absolutely certain that our model is properly capturing what our data is doing. If it doesn't, we're not allowed to capture it. And then again, backpedaling to those other models from those other softwares, they don't tend to do that.
Mhm.
People just look at this table, don't think was the variance equal or not, and just say, oh, it was not significant, there's no difference, and that's my conclusion, even though they are not capturing what your data is properly saying. You know, they're not listening, I would say. So that's the overarching idea. Also, just to explain the F value once more. So, if there was no difference between the two groups, it means that these groups would be relatively equal, would also mean that they don't differ from this grand mean. So this sum of squares, the difference would be about 0. The mean would also then be about 0, and I would get an F value that is very close to 0. Under the null hypothesis, I can, purely by coincidence, sometimes get F values that are not exactly 0. There has to be a very small difference purely by coincidence. It won't exactly be the same mean always. So even though that there is a small chance, this is the null distribution of the F value, which tends to look like this most of the time. This is the density or the chance that you would observe a value like this, and this would be the F value. 0, if there was no difference, that's what you most likely would observe, right, in this case. But the higher the F value, the less likely you will be able to observe something like that under the null hypothesis. And if the chance is smaller in this case than 0.05, we would call it significant. Because the chance is so small of observing this while the null hypothesis would to be true, that I have no choice to reject it in this case. Well, as you can see, we have a lot of variation. If I just look at supplement itself, just like last time, so I wouldn't be able to reject the null hypothesis because indeed there is a lot of spread, you know, in this. If I just pull everything together. But it is because part of the spread is these data points tend to be lower because they're likely in they had a dose of 0.5. So the other part of the variation, I'm not going to do the whole term for this, would then be the difference between the doses, as you can see. That would also be cause the difference between the groups that I can sum and would have, as you can see, a very large effect because it's also quite comparatively a lot more clear that there's a difference between the doses compared to supplements. Yes.
So is that one, the left one being not significant, is that related to the standard deviation being larger than the group difference?
Yes.
Okay.
Yeah. Because that by itself, indeed, like I said, it's almost equally large. And if I didn't have extra information, like why some data points are lower, then yeah, I wouldn't be able to explain it. So how does it have? Because these are two independent effects. And as you can see, they explain both a portion of the variance. This residual is the amount of variance that is not explained. So the squared difference between each data point and those group means. How much variance is not explained. And that's used to then calculate the mean square difference. And that's divided to get the F value. The more variance that is not explained, the smaller the F value, the close to 0. But the nice thing, however, is, just like last time, I'm able to combine these effects. And now I notice I don't have it. Oh yeah, I do have it, never mind. I do have it here. So as you can see, if I combine both of them, I explain a lot more variance. And now, this supplement, if I divide it, it's a lot smaller than explained variance. And it is a lot more significant, because I explain where part of the variance is coming from. And it's also what you see here. If I look within each dose, to the effect of supplement, it is a lot more clear. The variance is now a lot smaller because I explained why there was a whole bunch of data points down because they all had a dose of 0.5. Now it is much more obvious why there is a difference compared to before, where it was like this large of a box plot. So that's the idea behind this whole thing. That you explain both of these effects independently, and you sum them, and well, that's explaining why why there's a difference. If you look at
What was the test you did on the previous slide?
the same, also f-test. But then I only considered supplement.
Okay. Yeah. Okay. So you did.
It's also not something you would do.
You gave it like a lump. You build the data, put that into the ANOVA, and then you don't get as big. Okay.
Exactly. This is purely, you don't do this, by the way. Just I mean, you can if you ignore those. You can, of course. But why would you ignore those? Because those has an impact, and it helps you to show better why there's a difference between these two groups, right? Because it's quite more clear if you compare those instead of having all these data points on like one pool. So that's the idea behind it. That if you explain both of these effects, the effect becomes more visible, both if I indeed plot it, but also in terms of testing. And that's also what the ANOVA table does. It just gives a general overview. Does this variable, does this thing, does it explain something about my data? Or is it just randomness, why it's higher or lower?
So is this an ANOVA or is it still an ANOVA?
This is all our ANOVA, but we tend to give it for people names. Like ANOVA, if I have a continuous vector and a, a normal vector.
Yeah.
Multivariate ANOVA, if I have multiple vectors, multiple variables that are groups. And you have multiple linear regression if you have multiple variables that are continuous, basically.
Okay, but because those is not continuous, it's
Multivariate ANOVA in this case, yeah. But I mean, if you say ANOVA, this is just an ANOVA
The
table.
model always gets, like you always put in model, and you can always put in ANOVA in R.
Exactly. That's the whole thing. The most important thing that you realize here is that the structure is linear. It's normally distributed, and that's why you get a normal ANOVA table with an f-test. If you put a Poisson or binomial in ANOVA, and then you have to also use the ANOVA from the CAR package, you get a chi-square test because it doesn't act like these differences do not act like like an f value. They act a bit differently. They are counts. So yeah, and they scale with the variance. So you have to approach it a little bit differently. We're not going to go in detail on that because then they would be way further. But at least it helps you to still get an idea of if there's a difference or not. The interpretation of that table, ANOVA table, is generally the same. There is an overall explained variance by this vector, but it's easiest, as you can see, with just normal data. That's why we show it. Yeah? So this also starts to make sense in terms of a test for you.
Yeah, so I think I fundamentally misunderstood what LM was doing in the previous assignment.
Yeah. Because this is indeed what GraphPath or SPSS is just doing. You toss the data and you don't even see this whole breakdown of data points. It just shows you this and that's it, And if you don't even know how it's breaking down, that's the nice thing about R. It shows you exactly how it's breaking down. And it's easier to notice if you also misspecify things, where in GraphPath you cannot notice. I mean, you also just see it as an effect. But of course it has its advantages. Well, one thing before I actually get to a break, or I don't know if we can do a break, is, as you can see, it doesn't perfectly capture the data. There was a spike in one of the diagnostics, one of the plots, which you can still see here. You see that if I would simply sum these two effects, I get a mean that is about, 28. But if I look at the data points, they tend to be quite lower than that mean. If I look and compare this, actually these groups, they do not differ as much. If I just look at the data, they tend to be quite equal. But because I say the effect has to be consistent, the sum of these two, it is higher. So that also led to why the model was not fitting perfectly. I had this spike in there because of these groups, very likely. But to explain that, I have to get into what we call interaction. I do it actually the other way around, just because we're building up a model, but also in advance saying Normally, if you have multiple variables, you would actually do it from top down. First, examine an interaction, and if there's no interaction, then you examine the separate effects for that reason. That's something I will tell you.
Maybe one general question.
Yeah.
Can you get significance from the f-tests if the residual sum of squares is larger than either of the effects?
If the residual sum of squares is larger than
Like
either,
it was like 3,000 now. It was like higher than 2,426.
it is, as you can see here.
Yeah, for one of them.
Yeah, for one of them.
But for both, because then.
Oof. I think so, yeah.
Okay.
Oof, that's a tough one. Because it's partially the distribution of the F, it also partially depends on how many data points you have and how many groups there are. It tends to be like that if you have few groups and a lot of data points, but at some point sort of becomes detached from the x-axis and then it moves along.
Okay.
So it makes it a bit more difficult if you talk about case like this. I think you can, but then you need a lot of different groups.
Yeah.
And then I think it's also more, not one of these would be very significant,
Yeah.
but like, you know, a bunch of them combined will be significant. I think it's a lot harder to interpret. Just also, lastly, to finish this part off, you can then, if you decide, you see one of these covariates being significant, you can do then pairwise comparisons to determine where's the significance coming from. For the difference in supplements, doesn't really make sense. You get also the same p-value as before, because obviously that difference between the groups can only come from one thing, which is the difference between OJ and VC. You only have one group after all. So this indeed will be this t-test. But for those, it will be, of course, more interesting because you have multiple groups. Which of these groups are different and by how much? And you see also those estimates, they're basically the estimates that you got from your table because they're basically breaking down the data points, right? And having a certain mean based on that. So the difference would also be the difference that you had before. And that's, you can test then if this difference is then significant. Either pairwise or you can do it between like a single control, depending on your research question. I would say, based on this model, which is, as you may have noticed by now, not a perfect fit, that there is a difference between those one and those two, but if we looked at the data, it wasn't that obvious. So we would have to consider something that we call interaction first, before we can actually conclude that. Do we want a break, actually? Otherwise, I mean, I'm good to continue. No break? You're all fine? That's good. Then we continue. So what do I mean by interaction? Last time we talked about interaction as there being a change in the slope, right? We had a separate effect of age, we had a separate effect of a certain treatment, and if there was no interaction, then yes, there would be maybe an effect of age, it would go down the outcome with age, and there would be a difference between the groups, but just like now, it would simply be the sum of the two effects. The curve would be the exact same, basically, it will be parallel. However, if I had interaction, it would lead to a change in the slope. How much these two groups differ depending on what age I'm looking at. If I look at a low age of about 20, they do not differ that much. Whereas if I look at a higher age of about, 80, there is a lot of difference. That's what we call interaction. The actual effect that these variables have depends on the other variable that you're looking at. The same applies when we work with these groups. If let's say I have two poison, so poison A and poison B, and I look at, how much that they are causing, just, count the number of people that are dying if I give them the poison. Of course, some people are naturally dying, but if I give them poison A, as you can see, a certain amount of people are dying. If I give them poison B, also a certain amount of people are dying. There are multiple things that can happen. Either, if I combine these two poisons, they are just like before, what we have considered, I simply sum their independent effects, and they are simply additive. A lot more people are dying because of it. However, in practice, you may have noticed, especially if you work in pharmacological stuff, you may notice effects are not always simply the sum of them. They can boost each other, be synergistic. Maybe one of the poisons is breaking the blood-brain barrier and then the other poison can get more easily into it and cause more damage. and therefore their combined effect would simply be a boost, a synergistic effect. Or maybe, if I apply both of the poisons, maybe they molecularly, they like to stick together, so they wouldn't cause any damage at all. And instead of seeing the additive effect that I had before, I would simply see no change actually in the amount of death that I would have. A common example of this one that is always used, at least in pharmacology, is methanol and ethanol. Well, ethanol people don't consider, well, the average person doesn't consider it poisonous. Methanol people do. But methanol and ethanol, if you have methanol poisoning or suspect that, methanol and ethanol both bind to the same binding site in the liver. They compete for the same binding site. So if I would have methanol, poisoning, and I would be afraid to go blind or whatever effects you would have, if I just drink ethanol, it would basically compete for that binding site, and the effect of methanol that it would have is a lot less, actually. So yeah, that's just one example, but a lot of compounds can be antagonistic, even though they would be toxic together. Separately, if you combine them together, they have some kind of interaction that makes them, to have not as much of an effect at all. So that's also the case here. If you have a sort of combination of these groups, you would see an effect that is much higher or lower than you would expect as if you were to simply sum them together. That's the idea of a interaction between two factors, between two groups. It's a sum, a specific combination, not a change in the slope in this case. And you can even go with 3 variables, like if you had another poison and you have specific combination for each of them. Don't overdo it, of course, but you can get very, very detailed with this. So how does it look if I have this model from before with the genotype and the exposure? Remember, previously I would have an effect on the muscle of the muscle would be more developed in mutants. Treatment would increase in muscle efficiency. Well, maybe if I combine this, maybe something is opening up in the mutants, allowing the treatment to work better. So there's not simply a sum between these two effects. There is some additional effect that is the combination of specific treatment and mutants. And this is what we call an interaction effect. There's some combined extra effect going on, not just simply the sum of these two effects. However, maybe what if instead they target the same thing? Maybe this mutation is causing an increase in muscle, but also makes it the mouse not as targetable anymore for the drug that you're using. So even though I had a separate effect of mutant and drug, if I combine them, I don't see much of a difference. Actually, the combination removed part of the effect because maybe it didn't actually, affect your treatment as much. So you would have, compared to the overall, if I would add everything together, you would have a decrease because maybe there's no additional effect. How you would interpret this is purely biological, right? I cannot tell you why the effect is lower than you would expect. That you would have to look into biology yourself, interpret, making your hypothesis, and make an experiment on top of that. I can only simply say the sum of these effects are not what you would expect, and that would tell you something. You would have to find yourself out from a biological perspective why this is. We cannot help you with that. Well, we can help you with the models afterwards. So if I now look at this model before, it's the exact same as you had before, right? You have your starting point, the first group combination, so you had your dose 0.5 and you had your OJ, which would be about, in this case, 13.2. You have the effect of sub VC, overall it tends to be lower than OJ. And you had your effect of dose 1 and 2, which increased the overall length, right? But now we have something extra. We have interaction terms, which basically means there is a group-specific effect. If I have this very specific combination of VC with dose 1, I have to remove, in addition to what I had before, I had to remove 0.668 or 0.7, which is not, as you can see, it doesn't differ from 0, it's very small, but I would have to remove that to get to the exact mean for this very specific combination. Well, that's negligible, doesn't really matter, but if I look at group 2, those two VC, as you can see, I have to add 5.3. And if I compare it to before, for all the other groups, I removed 5.3. So basically, for that specific those two, I sort of cancel out this effect. If you want, I can also draw it per group. Are you interested in seeing the group means again, or? I can at least wait. I can just show it like this. And just follow along. So how is this model now looking at my data? Having this extra flexibility of making specific combinations having their own mean and not simply be the sum of the effects. So I have my OJ VC 0.5, OJ VC 1.0, and I have my OJ and VC at 2.0. So again, I start at, what is it about? 13.2, right? That's OJ at 0.5. 13.3. It's a bit higher than previously, but the model also changed with this extra flexibility. Sorry, 13.2. If I want to go from OJ to VC, I would have to subtract 5.3. So then I would, in this case, I would get, I have it nicely here, 5.3, 7.9. And that's not, it's a little bit different, but not as different as previously, right? There's some consistent reduction. If I want to go, instead of, instead I want OJ at 0.5, but I want OJ at 1, I have to add, starting with the intercept, I have to add the effect of dose 1, which would be about 9.5. So, starting from here, plus 9.5, which would be about 22.7. 0.7. So as you can see, it's a lot higher. Is there a specific combination effect of OJ with dose 1 that I have to add? No, right? I only see something with VC and dose 1. So there's no specific combination. This is just it. It also means that this effect that I had was specific for OJ, this increase, as you can see between the two. If I go then to OJ dose 1 to VC dose 1, well, I already added the dose 1 part, right? So now I have to remove the VC part, so which was minus 5.3. So I add minus 5.3, which is about, what is it, 16.9. However, as you can see, I'm looking at VC and 1. Is there a group-specific effect that I have to include here? Yes. This specific combination of VC and dose 1 leads me to have to remove an extra 0.7 from this formula. That's also what you see here, right? I added, I do minus 5.3 because it was VC, but I have to also subtract 0.7 because it's this very specific combination of VC and dose 1. These are combination-specific effects. So in this case, it would be, I probably also miscalculated already because it's not 0.7 added. It is then a little bit extra lower of, what is it, 17 or 16.7. Does this likely matter? No, it's very small. It's very close to 0. It's also, if I would base it just on this test, it wouldn't be significant. It's not significantly different from 0, but it is an effect nonetheless. You know, it's at least based on how this model looks at finding it. But then comes the most interesting one. If I go to those two for OJ, I just start again with the intercept. I only have to add the effect of those two, right? There's nothing else related to OJ, which would be about those two, OJ, 26. What is it here? 26. However, I now want to go to VC. So what do? I have to subtract the effect of VC, minus 5.3. So minus 5.3, because the effect was at the base is what we considered consistent, 5.3. But now I look down, is there a specific combination effect that I have to account for? If I look, yes. If I have the very specific combination of VC with those two, I have to add 5.3. So minus 5.3 plus 5.3, what happens in the end? It is the same. Also 26 in the end. That's what an interaction does. It gives a group-specific effect. It's not simply the sum of the two effects. There is some extra thing why this group is, why the specific combination is different. And again, this is not something you have to know like this, you don't have to do calculations like this and all that. But that is how R breaks down this, or any kind of software breaks down your data points into effect sizes that it then does to perform tests. Yes?
So you have two groups and two treatments like these, so it's better to include the interactions terms?
Yeah.
Instead of like the previous one?
Exactly. What I always do, because the model that I had before, it was relatively okay. If I just looked at it, of course, overall, this mean was a bit higher than the other one, but there was also some variance. So I would say it is okay. But if I just based everything on this model, I might have missed that indeed, yeah, there might be a consistent, that this group may consistently not differ if I don't consider that at first. And yeah, that's the danger that you can do if you try to model what we call model up from the start. You might miss something that is, very specific. If you model down, you start with a full model and consider this interaction, then you first consider, is there like group-specific effects? If there are not, then you can safely look at the individual effects of dose and supplement, because there are no group-specific effects to consider first. That's why I always go, when I start, with the model with interaction, the most complex model, and if I can, there's no consistent effect, group-specific effect, then I simplify it, I remove it, and I go to a model like this to examine these independent effects of supplement and dose. Because otherwise, indeed, you may have missed it almost, if I just went here naively. Yeah.
So in this case, like what we see is that they actually are converging, and now that we're using the effect, like that we're accounting for the interactions, we can see that.
Exactly.
And so as soon as you build your model with like that LM statement in R, as soon as you will increase an interaction between something, you will always get that in the summary as well,
Yeah.
I'm guessing, right?
It will always try to flexibly model this and add the term. If you add...
The output, you will always have like variable 1 colon variable 2.
Yeah.
Yeah.
And the thing is also, you have to add this interaction term, as you can see here.
Yeah.
It's not sub and dose, there's an effect of sub. And you can be very, very creative with this, because sometimes I work with replicates, and that can have some replicates, the signal was higher than other. It's nice to add to my model, because maybe it explains something, but it shouldn't really affect any of my treatment. It should be still consistently higher. I can add it without an interaction and see if I can explain some variance with that, and then focus on the actual interaction and effects with that if I'm interested in it.
And if you don't get any significance, like is the case here for sub PC with those 1,
Yeah.
then does that mean that like you then you can like save to ignore that?
Safe to ignore, I wouldn't say. It's still used for contrast afterwards, but you can indeed, at the end, when you do your pairwise comparisons, I already know that the difference between, VC and OJ at dose 1 will still be this 5.7. It will be not more or less than that, because here it's already not significant. It will still use this also for the pairwise comparison, because you assume that there can be a difference, but it will likely not cause any additional significance from what this already was. Yeah. Yeah, that's the idea of what we're doing here. You see also, if I do this spike that I had, because this one group was not modeled very properly, is gone. It's now almost a perfect fit, as you can see here. Or, I mean, this is one of the perfect fits. I generally don't get data sets that look as beautiful as this one. Yeah, it's sometimes I see like all these graphs. This really looks beautiful, actually. Can we always capture everything? You can't, especially if you work with observational data. There are a lot of underlying factors that you're not capturing, underlying interactions, and that's fine. I mean, that's why we're scientists. We don't have the full answer, and maybe some other study comes along that studies this effect and maybe like, oh wait, I see this now, this difference that there was that this other study didn't consider. That's the beauty of why we're doing science. This model that we had before is not completely wrong, but because we weren't considered this extra piece of information, we were not very complete in all our inference that we had. Having this extra information, we are able to more accurately depict what our data is telling me, and then also more accurately depict the kind of difference that are between the groups. Yeah?
And like, if I remember the way that this looked earlier, I'm like in the QQ plot, we now don't have that crank anymore. That we
Yeah. The crank really was because of the group.
Okay.
Yeah.
Yeah, okay.
Now you notice it quite a lot, right? If you see it comparatively. But that's also why most people with the first QQ plot wouldn't make it a huge issue, because it's just one group that is different. So it's also not that huge if you pull everything together. That's why it's more safe to go from top down, so you don't miss the effect if it is important for your conclusions that you're making. Sometimes it can be really obvious, you're missing an effect and that causes a huge shift, nothing is nice. But sometimes it can be quite subtle because it's one specific group that isn't, modeled properly. And given the natural variance that we have and how ugly real data can be, yes, that can easily be mistaken, I have to say. Yeah. I already explained these, right? Again, the rest looks beautiful, but now also the residuals are normally distributed. So now, if we look at the F-test, there's not just the effect of supplement and the effect of dose, but there is an extra value combined variance. There's something extra that has been explained. This was not now 800 before. Some extra variance has been explained by doing that. And we all know by now what effect has been explained, which is why the data points in group 2 were lower. So again, just to show, these were the individual effects. But now we're saying, hey, if I just sum these two individual effects, then it was higher before. I would predict it to be higher. But if I look, give it the extra flexibility to the size itself, it is lower. And that reduction explains also part of the variance, which if I do it per data point, square it and sum it, would be about 108, which is of course a significant effect. Yeah? Again, just like before, if it is not significant, it doesn't automatically mean there's no interaction, and none of the groups are different, because this is just 1 out of 6 groups that have this interaction going on. So yeah, don't just stop here if this is not significant. It's a nice indication. It's nice if you have many variables to do some selection of which are interesting to further explore, but it's not the be-all, end-all. It's just an indication. And that's also back when Ronald Fisher decided on all this, the model statistic structure, was the whole concept of why he made the p-value as an indicator of what is interesting to further pursue, not as a be-all, end-all conclusion. But unfortunately, most journals do it, so we have to abide. Okay. Now, we can also, again, do a contrast between the different groups. And you can, if you want to, all pairwise contrast, make all combinations of OJ dose 0.5 to VC dose 1. Most of these are maybe not interesting for you. At least I would be interested in the specific difference between OJ and VC dose, OJ 0.5 and VC dose 1. As you can see, it's very chaotic, all these tests, and very inefficient, because I do a lot of tests that are not interesting for me. I also have to apply multiple correction for all of these tests, which make them a lot less significant. Although I see a lot of them are quite significant. So, more interestingly is to very specifically specify what I'm interested in. I want to compare supplements pairwise, per dose. That's what this indicator tells me. Compare certain groups within the level of another group. So for each of the doses, it now compares OJ and VC, which is first of all very much organized, but also makes more clear what we were seeing before. OJ and VC in 0.5 and 1 had a difference about 5, with the other one being a bit larger, if I would simply sum this. Both of them were very significant, as you can see here. However, thanks to this interaction term, if I now look at those two, I see this estimate difference between these two groups is very small and totally not significant at all. So I can conclude that if I want to use the same, if I want to switch to OJ instead of VC, if I give them a dose of 2, there will be no difference in tooth length. So if that was my goal, then so be it. Then I can simply use a dose of 2. As you may have noticed, It's the same conclusion as last time. However, now it's quite very specifically on this group, where last time we were talking about curves that were sort of intersecting with each other. And now I just very specifically detailed these two groups are different, specific only for those two. Yeah? If I don't have an interaction, I can also do this. So the model before, I can also still do this. Would it be interesting? No, because then it would assume that the effect for each of these doses between OJ and VC is the exact same. It's exactly 3.7. Yes, I can do that, but what's the point at that point? Then I might just do only sub and that's it, because the effect is all the same between the groups. It's only interesting to do these specific comparisons if there is a significant or if there is an interaction going on. Yeah? That's the idea behind it. And what test you want to do, how you want to specify it, that's what we call researcher's degree of freedom. Is fully up to the researcher and their PI. They should also steer a little bit and not let them fully decide. And of course, statisticians if they're involved in the project. But other than that, it's fully up to yourself whether you want to go for something like that and just dig. And I have colleagues that do that actually from their other programs that they're doing. Or you have a very nice specific set of tests that you're interested in. And what I would at least recommend you is plan this. Pre-plan this before. What test are you interested in? Are you interested in all these specific combinations or only a specific set of tests? This is what we call, even if this was not a significant interaction, doing these tests here is still interesting of me. This is what we call planned comparisons. These tests that I am doing now, I beforehand decided that these were of interest. So these I carry out regardless if that interaction term was significant. And these are also the tests that I will report. I can also do that, but it's a lot more chaotic and I cannot really recommend it to do it. But again, researcher degree of freedom, you're free to decide what you want, and then some statistician will crack you down on it when they read your article. Let's see. So the last thing that is probably of interest of you is then also how to report this. Well, for reporting statistics, usually you can just open a journal and it gives an example of, you should say F with the degree of freedom, P is then this, and this is how you report a t-test. So just open the journal and look how they report their test. However, the most interesting part is how to visualize what you get out of it. And last time I already showed, with the help of plot model, ggplot, the output from EMEs, you can create very easily nice plots using this plot. It looks very big, a lot of code. It also didn't fit with the actual plot, so I spread it over 2 slides. But if you think about it, I'm just splitting this in 5 actually, 5 different parts. The first part is me just explaining what's on the x-axis, what's on the y-axis, and how should I subdivide my plot. The second part is layout, right? Just what theme I want to use. There are a lot of themes. My favorite is W, but you also have minimal that I have a lot of colleagues like to use, or a lot too, because we don't have a lot of people with R. That they like to use, and you can very specifically say what you want to do, how thick your lines want to be, your axis lines, how big you want your thing to want to be. If you think that I shook this out of my sleeve and just typed this in one go, no. I just said I want to do this. I Google how to make text bigger for the x-axis, and there was someone that said you need to use axis title X with, well, the what thing that you want to do. There are a lot of guides, especially for ggplot online, how to really in detail customize your plot. You have to do this basically just once, because once you have the setup, you can use the same plot with a different means object and plot the same thing. That's the nice thing about coding it instead of manually making this graph using other kind of graphical software. You had a question?
Maybe more of a general observation about our syntax. So this means that even if you have like a plot statement, you can add stuff on. Yeah,
that's the nice thing. It's modular, ggplot. So the thing is,
it's very different from other programs.
I know, that's the nice thing. It's very it's the first time you look at it, it's weird, but it's actually super nice. It's very modular. I could also, and that's what I did, I took this whole plot and I stored it as a variable. And even if I use this variable, I can then plus, and I can add other things on top of it. That's the nice thing, it's modular. You can just add, plus this. If I want to change the x-axis, plus, or y-axis, plus this.
Sorry, the value variable being p1.
Yeah.
Okay.
I can even store it if I want. I mean, you don't have to, but I like to store my plots in the environment and call them if I need them. So yeah, this is the first part, so all layout, as you can see here. The second part is where I use my means output, the predicted means and confidence interval, to basically plot a bar plot. And my data points, the original data points from the TootPro data sets, I use GGB Swarm. I like that because it sort of spreads out your points. Error bars with the lower and upper confidence level, which I got from my means object. And then some extra flair, change my y-axis, break it up into 10 pieces, change the palette to something that is more colorblind friendly from the R Color Brewer package. There are infinite possibilities, and I'm not going to say you have to make your plot like this, because it really depends on your taste, on how you want to make it online, what your PI likes, how you would report things in your type of, in your type of field. But this is at least what I like. So I have now I call in the P1, which is just the plot, so I didn't have to say the whole thing again. And now I have my bars, which show the estimated marginal mean, the mean according to my model. I show the data points, so I can also nicely show how that mean relates to what my data is actually showing, and the 95% confidence intervals. As you can see, they overlap a little bit here, but these were, as you remember, still significant, and I clearly see this model was very well able to capture my data, and yeah, it looks quite nice. The other thing that might also be nice, if you want to save it, you can do it in high quality format using ggSave. So I can say plot P1 I want to save called output TIFF, or SVG, or any other type of format that you use for imaging and editing. If you use SVG, you can actually split the plot into individual objects, so you can really make a detailed plot for yourself. You can, for certain journals, adjust the DPI, widths, heights, all that, so you make it, nice for yourself and optimal. And lastly, because I'm still here with scientists and they have to report in journals that like p-values, and I don't like it, but you have to add them usually. There's a very nice package called ggsignif, which you can very nicely state pair each of these groups, which you would then say 1, 2, 1 being the first one, 2 and x max 2. So this basically say, I want to say this one to this one, then again 1 to 2, and then again 1 to 2. This is the y position, so the height of the bar for each of these, as you can see, and then the annotation, which usually people do by stars, so just saying NS, or you can even say specifically the p-value. You can even go as far as automate this from means, it's all objects, but I don't like to do that. I like to know exactly what I'm doing. So yeah, that's you just have to play around with this, I would have to say. It's an example. If you have ever problems, do not hesitate to email me or just to look online. Yeah.
Why are there these different rows of these stars now?
Because there was rounding. It's not exactly, how to say it, 21 point something something something. It's 21.2. And these were all rounded to the same value.
Scale ruler.
They're not very precise. Yeah, it's partially precise. It's now a bit more noticeable with the GGB swarm, which, as you can see, nicely spreads out the points, but it also makes it easier, to see that values can be exactly the same, because it's not super accurate.
But the stars, they indicate significance, right?
Yeah.
So it's...
Well, those are the data points.
Those are representing the data points.
Yeah. These are the representing the data points. This
So
is
they
the
don't have
confidence
anything to do
interval.
with significance or not?
Huh?
So they don't have anything to do with significance or
No.
not? Oh, okay, that's a bit confusing, I think. Because it's like stars
I
and
mean,
stars. Yeah, okay.
That's what they want.
Okay.
That's what the journals want to see. You can do a box plot.
I think they're not stars. They're dots, and the significance ones are stars. But
I can see
Sorry. These are all these are stars. Yeah, it's pretty
That's why I
small.
was confused. Like, what's,
No.
like, why are there 4 stars?
I know in the presentation it's quite annoying to see, so I also output it myself
Yeah, no, but
in a
that was
higher
the
format.
thing I was missing.
Let's see, I have it here if you want to see it. So this is if I actually output it in.
Okay, yeah, makes more sense.
Yeah, right. That's I consider myself this to be nice, but of course tastes differ. If you find it ugly, well, so be it. Yeah, make it better yourself then. But I think this is nice for what I would how I would report it overall. Yeah, I mean you can do a lot of extra things like as you can see I also made the bar slightly translucent, which my PI doesn't like, but I like it, so I always do it. So it's fully customizable to your own taste, and the nice thing is again you just make this template once and it's easy to adjust for any type of model that you have. I just copied this from my own I made bars plots before, which I mean I can also show just for funsies. Let's see, this was from actually a recent experiment. I copied this actually for making the presentation. I think it was this one. I just copied the structure basically from this and just adapted it a bit for the data. As you can see, the whole thing was the same. And yeah, I don't like the p-value bars, but my PI wanted them, so I added them. Even though I find it stupid to do like millions of p-bars, but whatever. That's for her, not for me. Okay. So this also, way to end, is also a bit of a summary of the workflow, because I've now shown you how I would tackle a data set like this, analyze it, but it also brings me, hopefully, that you see some consistent pattern in what I'm doing. So you first load your data, you examine, and you have some kind of premonition of what's going on. I saw already at the start, when I looked at this data set, that indeed there appears to be some difference at the earlier dose, but not at the later dose. So you make already some kind of observation. Based on how the data looks and what kind of things you see in there of interest, you make a model, you construct it, you inspect the model, you perform model diagnostics, you perform a test like the omnibus test, a general test to see what things are more interesting to pursue. You can simplify the model. If the interaction was not significant, we can theoretically toss it out and focus more on these individual effects. But it was. These effects, whether I saw a difference between OJ and VC, dependent on which dose I'm looking at. So to toss the interaction out doesn't really make sense. It is part of what my data is showing. But you can, if it was not significant, you can toss it out and look at the individual effects. Do always make sure that you recheck then if the model is still fitting, because some variables are still important for fitting a proper model. And based on that, if you have your final model, your model that perfectly captures your data, at least you're satisfied with it, you perform the actual pairwise comparisons of interest, and then you report effect sizes, comparisons, and whatever you want that you want, and nicely report and visualize these results. So that's the overall workflow that I would have when I do modeling like this. So based on that, it's also like this. Are there any questions? Yes.
What we're looking at here is if you, like you're mapping all of the interactions and variables that you're aware of, right?
Yeah.
But if you have a distribution of data and maybe there are effects or like that you haven't yet annotated in the data, and so could you also use this setup to draw your attention to maybe underlying effects that you can then look into? Yeah.
When I do, for instance, a epidemiological study, when I have like a whole bunch of things, I toss literally everything in the model and just go from there, do an omnibus test, see what's interesting, toss out what's not relevant, and then continue.
Like for that, you already have to classify your data into like distinct groups, right?
Oh, if you don't have information about what's going on. If you do not have information, there is actually a type of models called latent models, which uses the information that is present in the model to capture if there's some underlying difference. There's actually a case, a very, controversial case that was doing it, because there was a model, I think it was from a Dutch model about reoffenders, and that model was actually quite racist to people, of color, that it would say that people of color would be easily to reoffend. So what did they do? They don't want to be racist, so they tossed that information about ethnicity and background out of the model. But what did that latent model do? Using the other information in the model about background, socioeconomic status, it derived that the person is likely black, and then, based on that, it still was biased against it. So yeah, there are models that can model these underlying patterns capture it using the other variables.
Like for this data, for example, let's say all of the tests were done on 2 different days or something.
Yeah.
And we're only looking at the differences between like orange juice and like BC and like the different dosages, but maybe there's actually a big amount of residuals being explained by the fact that it's 2 different days and for some reason that
Exactly.
yeah. Okay.
If you just have this model, you don't see that.
yeah, yeah,
And it's nice if you have that information, add it to the model.
yeah.
But if you see still clusters in your data, even after this, I have this model and I still see like a whole bunch of data points here and a whole bunch of data points there, it means there's something in my data that I'm not explaining.
Okay.
You can use a latent model to see if you can find that pattern, to see if there's something underlying or if there's some combination of the groups that may still explain this effect. Or you simply have to dig in your lab journal or field journal or whatever to see why do you think that these groups are higher or lower. This model is only capturing what you yourself are inputting. The nice thing, at least about R, is that it's showing you can exactly derive what it's doing. Unlike other software, it's just a black box. But still, your model is as complex as you make it yourself. Also, if you don't know exactly how your outcome works, because now it specifically nicely says, oh, this is normally distributed, this is Poisson and all. Sometimes I don't know if an outcome is exactly normal, or if it's Poisson, or if it's something else. In those cases, I always go with the simplest model first. The simplest will be simply normal distribution. If it doesn't work, then I add some complexity, go to a GLM or another family. If it doesn't work, then I add some other complexity. And sometimes I just have to toss it, say, I can't capture it. This is the best, most accurate representation of the data that I can give with the model that I have. I report it as transparent as possible, but maybe in a few years someone comes by with the perfect exponential family, and then that can. But sometimes you just have to make do with what you have, and it's unfortunate, but sometimes it do be like that. Yes.
More of a general question about ANOVAs.
Yeah.
I'd been reading up a bit, and I had read that some people feel that mixed models supersede the need for ever to even use ANOVAs.
Well, the thing about mixed model is that it's an ANOVA with extra variables, which we call random effects. Yeah, it's still at the basis how you would go about it. You can still treat it as ANOVA. You have pairwise effect. You post the canal. But what I was talking actually about replicate, right? That I could add replicate to my model. But if I add replicate to my model, it would cost me degrees of freedom. It would cost me extra, size. I would have to interpret it. But I can add that as a random effect, saying, there's some extra variance in the model that I know where it is coming from. I'm not interested in comparisons and all that, but I do want to capture that. And that is what you do with a mixed model. Sometimes it's also important, because let's say these guinea pigs, what if this that I have here, I assume these are 60 independent guinea pigs. But what if I only have 10 guinea pigs that over the course of time I expose to each of these different conditions? Do I then have, is it fair to say I have 60 independent data points and I have this much power? No, because I have only 10 guinea pigs. And a mixed model does capture that variation. It does then look within a guinea pig. How strong is the effect? Is it going consistently within the guinea pig, going up or going down? Which is, of course, much better to see than the effect, just like now. But it also corrects your degrees of freedom to not be 60, but instead be based on 10 observations. So in those cases, a mixed model is very important. But it is simply an adaptation of the model that we are already working with.
So it is a more flexible ANOVA.
Yeah. Basically, you can almost say most models are more flexible ANOVAs, or more flexible linear models. That's also what we call Poisson and binomial generalized linear models. They still are interpreted as a linear model. It's just that the underlying family is not normal. It's that, but the outcome, we still see those tests like we saw before. All these things we see for those two. They normalize things or linearize things. But literally almost all standard models that you work with, indeed also for mixed models, they do that, They simply attach to what we already have. You also would get an output like this, but with an extra tab. You don't only have residuals then as the random effects, but you also have like random effects for in this guinea pigs, simply.
So are there situations where it would be preferable to do an ANOVA instead of a mixed model? Like, can't a mixed model capture everything that an ANOVA can?
The mixed model may be more difficult to fit, but I think it's more the other way around. If you notice that your data points are not independent and you have repeated measurements, you have to use mixed models, because otherwise these results are biased, because you're saying that the effect that you observe is based on 60 independent observations. I have this much, information that says independently that there is consistently in this population effect. But if it's based on just 10 guinea pigs instead of 60, there is a lot more uncertainty about if I would apply this effect in a population, So that's why you have to use more a mixed model. It's more, if you want, easy is of course your ANOVA, but if you are dealing with complex structures like that, you have to use a mixed model. Yeah, that's more or less the idea, I would say.
And that's because the assumption of independent data
Is violated. Yeah. Exactly. So it all comes down to experimental design. That one, you can't really. I mean, you can tell partially in the data if I do see the clusters, but other than that, you simply have to know if you have to use a model like that. And I have colleagues. I remember that a colleague who was doing his analysis in GraphPub, by the way. Also, just again, he was measuring neutrophils within zebrafish, within specific tissues. So we'd have like 3 tissues per zebrafish, tracking 20 neutrophils within that zebrafish, and see if there was a difference then in like neutrophil behavior. But he was then having 1 data point per neutrophil for each, and saying he only had 3 zebrafish, but he had like 250 data points, and he saw, look, this treatment is causing a significant effect, but it's not based on actual variation in between zebrafish. That effect is based on, within a zebrafish, these neutrophils are, of course, very consistent. So you're not looking at the variation of interest. If your effect is consistent between zebrafish, you're looking at the effect if it's consistent with those 250 observations, if it's consistent between neutrophils, and that's not what you're interested in. But the tests were way more significant than it should be, and then you would have to realize, oh, I see clusters which are the zebrafish, and I should actually use a mixed model in this case and not do an ANOVA, because it's very biased and unfair in this case. And it happens a lot, I can say. That is unfortunate, but that's why we teach courses like this, to help to guide people to make better decisions and not just toss all their data in a black box and just do whatever it is they want. Yeah. Any other questions? No? Then I will leave you to this, to the assignments. Next week will be with Halana again, I think. She will talk to you about, what was it? I think publication grade graphics and Bayesian statistics a little bit, which is a little bit different from what we have been doing here. And the last lecture will be about, indeed, a bit more about experimental design. So how do we decide power, what's an independent sample, and also the kind of worms of things that we see go wrong when people design their experiments. And like the example I said just now, that they saw all the neutrophils as independent data points. How do we avoid that when we do things like this? Yeah? Yeah? See you, well, probably in 2 weeks, but for Alan, see you next week.